And OpenFlow controllers are sort of becoming like Linux distributions, where you have so many and there's one popping up every day. For example, Floodlight is a very widely used controller which is based on Java, and then there's Nox, which is a C++ based controller, and there's also one called Box, which is a Python variant of Nox, and then there's Beacon and so on. So if we merge this with the previous architecture of SDN that we saw, OpenFlow now becomes this interface between the data plane and the control plane, and the control OS can itself be Floodlight or Nox or Beacon or whichever controller that suits our needs. Now, while there has been a lot of research on developing new applications for the OpenFlow architecture, benchmarking the architecture itself, the switches, the control plane, etc., there has not been much work on trying to use SDNs or OpenFlow as an experimental platform for trying out new or non-IP protocols, and that is what we are trying to do here by trying to have a design by which we can implement the MobilityFirst protocol stack as an SDN. So when we consider MobilityFirst, it's some of the key features are the name address separation, where you have globally unique identifiers for each device in the network, and then we have a global name resolution service which resolves these GUIDs into routable network addresses, and that whole separation is sort of done with the key idea of being able to handle at scale mobility in the network, where end hosts can move around arbitrarily. And there's also in-network storage or buffers within the MobilityFirst routers, so that they can be stored for a while when you have scenarios where the link quality is bad. And there's also other enhanced services using service IDs and in-network compute servers, which can process packets as they go to the destination. For example, if you have a service which asks for some kind of video transcoding in a streaming application, then the transcoding can take place within the network by the servers themselves. So the idea that we have here is that there could be several MobilityFirst domains, and each individual domain itself could be implemented in any way. For example, one could be a MobilityFirst SDN which has a central controller and a bunch of OpenFlow switches, while the other could actually be traditional MobilityFirst routers running the distributed routing protocol. And all of these things talk to the GNRS. In the case of the traditional network, the routers would communicate with the GNRS, and in the case of an SDN, the controller will be communicating with the GNRS, and they should be able to work in coordination. So let's take a look at the MobilityFirst router, or what happens to packets in a MobilityFirst router, and what we have to do to implement it as an SDN. So in MobilityFirst, the L3 or the network layer PDU is called a chunk, which is composed of several link level packets. So as we see, when the datagram enters the router, it enters as an L3 chunk, which is composed of multiple link level packets, and the size of this chunk could vary anywhere from a few kilobytes to several megabytes in size. That could be based on the link quality or what kind of network we're using. And the first thing that the MobilityFirst router does is aggregate all of these L2 packets into an L3 datagram, and then this whole datagram is then forwarded to the routing module, which could do forwarding based on network address, or do a GNRS lookup to resolve the GUID, or decide to store and forward it at a later point if required. And then once a routing decision has been made, depending on the quality of the link or depending on the type of the link to the next hop, it then splits it again into appropriate size chunks and link level packets and forwards it out of the appropriate port. Okay, so if we have a MobilityFirst software-defined network, these are the key functions that the SDN controller should be able to do in order for the network to function. So the first thing is the controller should have a way to understand what GUIDs are and learn the GUIDs that are present in the SDN domain. And it should also update the GNRS about any new GUIDs that get attached or detached from the network. So that's the first part, that is to make the controller understand and learn GUIDs in the network. The second part is it should be able to set up MobilityFirst flows on the OpenFlow or SDN switches in the data path. So there are a few difficulties or restrictions in how we define a MobilityFirst flow, and we'll look at it in a couple of slides later. And then it should be able to do mobility management, which is sort of the key feature of MobilityFirst. So if an end host moves around either within the SDN domain or between multiple SDN domains, it should be able to handle such mobility. And the last part is providing these enhanced services such as in-network compute and in-network storage. So it should be able to coordinate and manage the storage and compute devices that are part of the network. So that's the overall architecture of the MobilityFirst SDN that we have. We would have a central controller and several SDN switches in the data path. And let's say if host X wants to, if the host wants to send some data to destination X with some kind of in-network compute service required, then the first packet goes to the controller and it has to set up flow rules appropriately to send the chunk to the compute server, which will then process it and forward it to the destination X. The flow rules for which again have to be set up. And let's say if it wants to send it to destination Y and the link to destination Y is down, then the controller has to make the decision that the link Y is down. And then instead of setting up flow rules to forward it to the destination, it has to be able to set up a path so that it gets forwarded to a storage node in the network and then gets forwarded later. So this is sort of the overall architecture of the MobilityFirst software-defined network. So the first part is, like I said, GUID learning, making the controller learn GUIDs. So every time a MobilityFirst host attaches to the network, it sends out these broadcast messages called link probes, which is essentially just the source GUID of the host that has joined the network, and the packet type saying this is a link probe packet. So we capture these packets at the controller and build a local GUID database at the controller, which has a map of what GUID corresponds to what MAC address, and then that can easily be resolved at the controller to a switch and the corresponding port or the attachment point. So this way, by listening for link probe messages that the MobilityFirst host send in the network, we can build a local GUID database at the controller, which can later be used to forward packets when we get actual MobilityFirst data packets.
So before you go,
Sure.
go back one slide, I guess. So the controller, not in this slide, but is the controller, you're assuming it's connected to GNRS as well? So what resolves the GUID to network address translation?
Right. So the way we do it is the controller does not have the GNRS inside it.
Well, okay.
Yeah. So the idea is if you have a GUID that is a packet destined to a GUID that's part of the same SDN domain, then the controller should be able to forward the packet just based on the GUID without having a network address. And if you receive a GUID for which you do not have an entry in the SDN domain, then the controller coordinates with the GNRS to sort of resolve it and then forward the packet.
So assuming the controller has some connection to the GNRS, you know,
Right.
in it, but
Yes.
Okay.
Yeah. So I guess this was the idea. So the controller of every domain talks to the GNRS
Okay.
whenever it needs to send packets out of the domain to another host.
But so if it's within the domain, how does it know? Does the controller have its own mapping of GNRS to destination, or?
Right. So that's the GUID learning process.
Okay.
When every host joins the network, it sends these link probe messages which it uses to learn about GUIDs within the domain. So once every host has sent those link probe messages, the controller has a map of every GUID that's present in its domain and what attachment point it's currently connected to.
So will this reporting to GNRS?
Right, yes. So it will also report these to the GNRS so that controllers or other MobilityFirst routers in another domain can use this in order to route packets into this domain. Right. So once we have a map of all GUIDs that are present in the network, the next issue is to actually define what a MobilityFirst flow is. So this is where we face a restriction in current SDN implementations or OpenFlow in specific, The problem is, while you can set up a flow rule which says, okay, if the destination IP address is 10.1.1.1 and the source IP address is 10.1.1.2, then you have to send it out of port 15. But there's no way to actually set up a flow rule which says if the destination GUID is XYZ, then send it out of port 25 or port 32. Because the switches only support IP-based flow rules. And the other restriction is that unless the ether type of the packet is that of IP, it won't even look at the IP fields. So when we say we want to define a MobilityFirst flow on these data path switches, we are restricted to setting up flows based on just L2 fields, and so we define a MobilityFirst flow this way. So each chunk of MobilityFirst data, which could be anywhere from a few kilobytes to several megabytes in size, corresponds to one MobilityFirst flow, and all of the link level packets that belong to the same chunk have a field called the hop ID, which remains the same for all these packets that belong to a chunk. And what we do is, when the source sends out MobilityFirst data packets, it tags all of the packets with the VLAN tag as the hop ID field, and the controller can then set up flow rules based on VLAN tags instead of using destination GUIDs or other identifier fields. So the flow rule would be, first we check whether it's a MobilityFirst packet, so we check for the ether type, and let's say the source MAC address to check which source this is coming from, and then a VLAN ID which identifies what chunk this corresponds to. So we have one flow rule per chunk which gets forwarded on the board. So this would be the data flow for one MobilityFirst chunk. So we have several link level packets. Say if it's a 10 megabyte chunk with the standard Ethernet PDU, we would have around 8,000 link level packets in a chunk, of which only the first packet has the routing header, which would be the destination GUID, the source GUID, and other L3 fields. So the first packet gets sent by the switch to the controller, where it uses its local GUID database to identify which attachment point the end destination device is connected to, and then it sees the VLAN tag on this first packet and sets up a flow rule on the switch saying, if you find this source MAC address and this VLAN tag, then you send all the rest of the packets on the corresponding port which goes to the destination device. So all of these two packets from link level packet 2 on to N match the flow rule on the switch, and they get forwarded by the switch without having to go to the control plane.
So this VLAN tag, the source has to know about what tag to put in.
Right, so that's why currently what we are using is we just use the hop ID value as the VLAN tag. So all the packets that belong to one chunk will have the same VLAN tag. So let's say the hop ID for one chunk is 100, then all of these packets will have the VLAN tag 100. And when the first packet goes to the controller, it looks at the VLAN ID field and sets up a rule saying, if you find the VLAN tag 100 and this MAC address, then you send all the packets out of that port. So these packets will match that flow rule and they'll get forwarded by the source.
So the source can arbitrarily pick a new ID for each chunk and then...
Right. So because for every chunk one packet will go to the controller, the source can arbitrarily pick whatever VLAN tag or chunk ID that it wants.
Arbitrarily, no, right? Because you can have collisions.
So that's why we match both based on the source MAC and the VLAN tag. So if there are two hosts sending with the same VLAN ID, then the source MAC would make sure that we don't confuse between the two flows.
What if you have two processes on the same node?
Yeah, locally you have to...
Yeah, so I guess when the same source sends two different flows, it will have to manage the VLAN tags in such a way that it doesn't cause a collision within the same host that's sending data.
Okay.
Right. So now that we can set up an end-to-end MobilityFirst flow on the SDN switches, the next problem is to handle host mobility, because handling at-scale mobility is sort of one of the key features of MobilityFirst. And in the context of an SDN, we can differentiate two different types of mobility. One is when a node moves from one attachment point to another, and both the attachment points are connected to the same controller. And the other is interdomain mobility, where it moves from one SDN domain to another SDN domain itself. Right. So when it comes to intra-domain mobility or mobility within the same SDN domain, the central control scheme sort of inherently helps us in handling this kind of mobility, because each time a device disconnects from a switch, or each time a device connects to an attachment point, an event is triggered at the attachment point, which sort of sends a message to the controller saying this host has now connected to me on this port. So these event notifications keep the controller up to date on what the network topology is. And in addition to that, we can use the link probe messages that the devices send each time they connect to an attachment point to sort of make sure that the map that we have is up to date. So let's say in this kind of a scenario, host Y moves from switch S3 to switch S2. When it disconnects from S3, an event that's an event for S3, so it reports it to the controller saying the device was removed. And when it associates with S2, that's an event for S2, and it reports that to the controller about the new device association. So the topology is now up to date, and in addition to that, when Y attaches here, it also sends the link probe messages, which are again captured at the controller, and so that updates the GUID database that we have. So every time a device moves from one attachment point to another, using the event updates and the link probe messages, we can make sure that the topology and the GUID database that we have is always up to date. So any chunk that comes after the event update is now forwarded along this path, because the controller will now set up a new flow rule on S2 saying you're supposed to send it on this port and not the port that goes to S2. So that's handling intra-domain mobility. And when it comes to inter-domain mobility management, so this is when there needs to be some kind of coordination between the controllers of the two domains involved in the mobility event. So for this, we have the Global Name Resolution Service, or the GNRS. So whenever a controller finds that a device doesn't exist for this specific GUID, it sends a request to the GNRS asking for the new location of the device. And since the device, when it attaches to the new SDN domain, the controller of that domain would have updated the GNRS saying GUID XYZ has now attached to me on this switch port. The controller of the first domain will be able to query the GNRS for the new location. So the routing algorithm would sort of be like, first it checks whether it's a hit in the local GUID database. If it is a hit, then it sees whether the device still exists at that attachment point and then installs the flow rule. If it's not a hit, or if it cannot find a device in that attachment point, it just sends a query to the GNRS asking for an updated location for that device. So this is an inter-domain mobility scenario. We have one SDN domain here with controller 1 and another with controller 2. And let's say the device with GUID Y moves from this SDN domain to the attachment point S3 on domain 2. So this triggers device dissociation, and controller 1 gets notified that this device has now moved away from this network. And at the same time, when Y attaches to S3 there, that gets updated into the GNRS. And when this controller finds that it cannot locate device Y within the network, it now tries to bind the GUID to a network address by sending a GNRS request. And the GNRS responds saying, okay, Y's new location is on that network, and it uses that to set up a path to the other SDN domain. Okay. So another key feature in MobilityFirst is that if the traffic is delay tolerant and if the link quality to the destination device is bad, then there are buffers within the MobilityFirst routers that will store the chunks for a while and then try to forward them later when the link quality becomes good again. So we need to be able to support this kind of a storage functionality in the SDN. But since the data path elements for us are just commodity OpenFlow or SDN switches, they do not have any storage built into them by default. So we'll have to use an external node or a network or a NAS box which serves as a storage server for each SDN domain. So some of the key things that the controller needs to do are just like the way we had a mechanism to learn about GUIDs in the network, there should be a mechanism to learn about the storage devices that are, or NAS boxes that are a part of the network. And then what the controller needs to do is every time it sends a chunk into the storage box, it needs to maintain metadata on what chunk ID is being sent to which storage device in the network. And the last part is a protocol that can send and fetch chunks based on chunk ID whenever the controller wants to.
So one question, why can't the storage boxes on a domain themselves, all of them have a GUID? Isn't that an easier way to do it?
Right, so that's one of the ways you could implement it.
Okay.
If you just have a GUID for a storage box, then I guess the link probes or the discovery messages will have to contain something, some additional field which says this is not a regular host and it's actually a storage node which the controller can send chunks to in case there's a device whose link is down. So this is a typical scenario where storage might be required. Let's say the source wants to send a chunk to X and the link to X is currently down. And if X is not associated anywhere else, then the GNRS is simply going to respond to the controller saying X is still connected to this domain, and the controller knows that the link to X is down. So it can decide to send the chunk to the storage instead of dropping it, which something like TCP would do. So when it receives a packet in with the destination GUID X, it sets flow rules on S1 and S2 to forward the chunk to the NAS box. And the controller can then, at some point of time later, it can query the GNRS to see whether X is associated with a different network and forward it later. Or if X associates with the switch on the same network, it will receive the link probe message from X, which can then trigger a fetch operation from the NAS box to forward it back to the destination. So the last picture is supporting in-network compute services. So this is again something similar to storage because the switches themselves cannot do any compute operations. So just like NAS boxes, you would have compute servers that are part of the network and will have some kind of a discovery protocol to tell the controller that this is the GUID of the compute server and it can receive packets for processing. So what we need is a discovery process to learn about compute servers in the network. And just like sending chunks to storage, the controller maintains metadata on what chunk ID is sent to which server for processing. And the last part is, in this case, we don't need a protocol to fetch servers from the compute server, fetch chunks from the compute servers, because once the computation is done, the servers can just forward it back to the destination, and that would be a regular MobilityFirst Flow role for the controller. So this is a typical compute scenario. So the first packet from the source would go to the controller, and looking at the service ID, it knows that it should be forwarded to a compute server and not to a destination. So it can set up a flow rule on S1 and S2 to forward the chunk to the compute server. And once the compute server finishes processing, it can then try to forward the packet to X, which will again trigger the controller to set up flow rules on S2 and S3 to set up a path which goes to the destination device. So the prototype that we've built is using OpenFlow 1.0 spec-based switches and the Floodlight controller. So Floodlight, as I mentioned before, is a Java-based OpenFlow controller. And what we've done is, apart from the core modules that Floodlight has to learn about the topology, we build our own MobilityFirst modules into Floodlight and extend it so that it can support MobilityFirst functions. So this is Floodlight's inherent structure that it has when you download and install it. So it has the OpenFlow protocol to communicate with the data path switches. And then there are its core modules on top of the protocol, such as the device manager, the topology manager, and the link discovery, which what they do is they respond and receive the control messages from the switches and build the topology or build a map of the entire network. And this is exposed to the upper layers where we can build applications which can be new routing schemes or some kind of a QoS service, or any network service that we want can be built on top. So some of the key changes that we made to Floodlight in order to make it support MobilityFirst are, the first thing is the Floodlight's core itself, because inherently it has a dissector which receives packet ends and tries to extract the IP-based fields from the packet ends, while what we need is a dissector which receives the packet ends and exposes MobilityFirst fields such as destination GUID, source GUID, chunk ID, etc. So we added a MobilityFirst packet dissector which does that. And the other things are more or less like application modules built on top of Floodlight's core modules and the packet dissector. So if the controller receives a packet in which the dissector sees is a link probe, that gets sent to the GUID Learning module in order to update the local GUID database, which is just a hash map of GUID to MAC address. And if it's a data packet, it gets sent to the forwarding module, which can set up flow rules based on VLAN tags. And then there's also a storage handler. So after we made changes, the structure looks something like this. There's Floodlight's core modules like the device manager, topology manager, etc. And whenever we receive packet in, that's classified into what kind of MobilityFirst packet it is. And if it's a link probe packet, it gets sent to the learning module, and the routing module handles the data packets. And if we see that a destination device is not found in the network, we currently send it to storage and use the storage manager to sort of maintain a map of what chunk IDs have been sent to storage so far. So that's the structure of Floodlight after the changes that we made to support MobilityFirst. Right. And so we performed experimental evaluations with this MobilityFirst prototype. So the two key things to evaluate are the control plane and the data plane. In the control plane, the main thing to look at is the processing delay, or how much time it takes in order to set up a MobilityFirst flow. So one thing is the processing time at the controller, and the other is the RTT for that first packet which performs the flow setup. So those are the two key parameters that we looked at. And then in the data plane, we look at the single flow forwarding throughput, or how fast the switches can push a MobilityFirst flow. And the second thing is what happens if there is a different type of traffic, or traffic which requires a GNRS lookup at the controller. And the third thing is what happens if there are multiple flows present in the network. So the first part is the control plane delay itself. So the control plane delay essentially is composed of these three components: the propagation times and the switch forwarding delay for the round trip. And the other main component is the processing time that it takes, that the controller takes to receive the packet in, look up the GUID in its database, and send the flow mod and the packet out to the switch. That's the processing time at the controller. And the third is the switch processing delay, which is essentially the time that the switch takes to encapsulate a data packet as an OpenFlow packet in and send it to the controller. And when it receives a flow mod or a packet out, strip out the OpenFlow headers and install the flow rules on the switch. So these are the key components. And the main thing that we look up, that we concentrate on, are the overall round trip time for a flow setup itself, and the processing time that the controller takes to receive a packet in and then send a packet out and a flow mod. So we did this by using TCP/DOM timestamps at both the source and the controller. So essentially we send 10,000 MobilityFirst data packets, each of which initiates a packet into the controller, and then it sets up a flow rule on the switch, and the acknowledgement comes back from the destination. So we found that the flow setup time, or the overall RTT of the first packet, was an average of 3.5 milliseconds with a standard deviation of about half a millisecond. And the time taken by the controller to process the packet, which is the time between the arrival of the packet in and when it sends the packet out, was around 0.1 milliseconds, or 114 microseconds, with the standard deviation of about 32 microseconds.
So what kind of machine was running that?
So this one was an i7 with 4 gigabytes of RAM.
So how does this compare with, say, the regular flow setup that takes place?
Right, so the time taken at the controller itself is not very different from a regular IP flow, because the only thing extra that we do here is we look up a hash table to map the GUID to a MAC address, whereas a regular TCP IP flow would use the destination IP address field to look up the location of the device.
Now, is that table kept in memory?
Yes.
Okay, so what is the size of a row in that table, and how many, how many flows can that support?
So the size of a row would be the size of the GUID field, whatever that we use. If we use 128 byte GUIDs or 1 byte GUIDs, it depends on that. So and then the size of the MAC address field for it to work.
What if the controller goes down?
Right. So those are some other reliability issues that we have to look at. For example, there was a defense yesterday which sort of saw how multiple controllers can coordinate between themselves to implement different types of services. So we could have backup controllers, or one controller which sort of handles only GUID based forwarding, and another controller which handles storage, rebinding, and things like that. So we could have some kind of a hierarchical structure to ensure reliability.
Well, to push on that a little bit more, so if there's some connection set up, controller goes down, and all that state's lost, is there some way to recover?
Unless we have a backup controller to which the switch connects to right away, I don't think it can be recovered. But those are things that exist today, as in you can set up a master controller and a slave controller, so that if one goes down,
Okay, is there some way for the client to recover in that case?
I'm sorry, the client to recover in the sense?
Well, let's say the client's sending some large message.
Right, yes.
And it's getting all broken into chunks, and there's a nice flow, and then one of the controllers goes down.
Right.
And let's say there's no backup. So then what would happen to all those?
Right.
So when the controller came back up, and it would see these packets, or when the switch, I guess actually if the controller goes down in the middle of sending data, it will continue. If the switch goes down, it comes
that's
back up,
when,
then the controller would have to reload all the moves into the switch. If both go down, right? No, I mean, that can happen, right? Both could go down, and then what would happen to that flow, I guess?
Or set of flows. So if you have a large,
I think the assumption is the OpenFlow controller can't go down, and you have to come up with replication and hot standby mode for that.
Everything can go down.
Yeah, but
You have to think about.
you just have to bring the probability down to 99.
Yeah, you know.
But this is the problem with centralization, which we don't necessarily buy into, but if it's a single domain.
So, one answer is, we haven't done that.
But if you try to do this for a large interdomain network, you have to address those issues. So I think Google has solved some.
there are interesting ways to do it.
But I mean,
but yeah.
So the original internet design, ultimately the client had to recover, right?
So this too will have that.
Right.
Or initiate the recovery or something.
I think there is still the option of the end-to-end protocol recovering from this, but unless it has alternate data paths.
So the simplest
which is different from
MobilityFirst
this.
transport layer has a kind of indicator of some sort. If it doesn't complete, it will try.
Right, right. No, I mean, if there's some multiple data paths, then the client can initiate some recovery. But you didn't look at any client recovery.
He was not.
Yeah, no, it's okay.
Yeah.
I mean, if there's multiple data paths, then I think the client doesn't have to do much, because when the controller sees that one of the switches is down, it can set up a flow rule on the other switch, saying the packets now have to go through
Right,
that
so
way.
unless the controller and the switch go down at the same time, then
That's
you
one.
wouldn't have that. Yeah.
And there are services like, you could potentially use services like Redis or Memcache, right, which are distributed key value stores kept in memory across a bunch of machines. So you could implement it that, I mean, there are interesting things you can do from a distributed systems perspective over here to overcome those issues. But nevertheless, it's a challenging problem, especially when you have a large set of flows active and things start going down. That's when things become very interesting.
Well, in IP, the ARP and DNS service can also.
Right, of course.
That's not
Yeah.
a typical source of many
No, but they push all those back on the client, right? So ultimately, the client's responsible for recovering its own flows.
Yes, recovery will be there here as well.
Right.
So in the data plane, this is a graph for the single flow throughput, and the x-axis is the size of the chunk that we use in kilobytes, which varies from 1 kilobyte up to 10 megabytes in size, and the y-axis is the throughput in Mbps. So the comparison graphs that we have here is the red one is just a network address-based flow, which essentially means the first packet of the entire flow initiates a flow setup, and the rest of the packets all go through the data path only, which would be a regular TCP flow. Or if we have an SDN switch which can actually understand GUID based flow rules. For example, if we set up a flow rule which says if the destination GUID is X, then send it out of port Y, then all the chunks can just go through the data path and we'll never receive packets at the controller during the entire flow. So that's the first line. And the blue one is a click-based software router, the MobilityFirst reference implementation on click. And we see that that actually aggregates the packets and then does the GUID binding and then splits the packets again and then sends it out. We see that there's not much difference in the throughput over the entire range of different chunk sizes. That's, I guess, essentially because the delay is in the entire processing itself, where we have to aggregate each chunk before binding it and then splitting it and sending back out. So there's not much difference in throughput. And these two are the other two are the OpenFlow MobilityFirst flows, where the pink one is just a GUID based flow, where essentially for every chunk the first packet goes to the controller and it looks up the GUID table, sets up a flow rule, and the rest of the packets go through the switch. Again, when the second chunk is sent, the first packet goes to the controller and that initiates a flow rule. So in that we see that when we have very small chunks, for example, if we have just 1 kilobyte chunk, essentially every packet has to go to the controller, sets up a flow rule, and then, so it's because of that delay that we have this very low throughput for small chunk sizes, because there's a huge fraction of packets involved going through the control plane delay. But when we go to large chunks of 8 or 10 megabytes, we see that the throughput achieved is almost 800 or 810 Mbps, which is close to line rate or close to what you would see if you could set up a flow for the entire data transfer. And the last one is flows that involve GNRS lookup. So the way we did this experiment was to simulate a delay at the controller, which is sort of the time it takes the controller to query the GNRS, get a response, and then set up a flow. So we use values from the DMAP paper of an average of about 80 milliseconds. So for that we see that the additional delay causes an even more reduction in throughput, and even for chunk sizes of around 10 megabytes, the throughput is only about 550 Mbps.
So the red line looks artificially inflated, since even if you have GUID based rules in the switches,
Right.
how will you put that rule in? You'll have to still send the first packet to the controller and...
Right, but once the first packet goes to the controller and we set up a flow rule saying GUID XYZ has to go on port 10, then even the next chunk will have the same GUID XYZ, so it can just go through the switch. That's more like just like an NA based flow rule, right? Where you use the identifier to set up the flow rule instead of a chunk per chunk flow rule.
Right, but that can be done in even your pin curve, where you say that the hop ID remains the same for all chunks from this source and destination.
Oh, no. So the hop ID remains the same only for each chunk.
Yeah, but
Right.
if we make a
Right,
scheme
if we make
then the
something
same
like
rule
that.
can apply to the next chunk, right?
Right,
Then
yes.
we
So
can
why
just-
don't you do that? Like my question was, why do you have to do it on chunk by chunk basis?
So the idea was, since the entire transfer in MobilityFirst happens on a hop by hop basis, we thought setting up flows on a per chunk basis would make sense. But if the entire domain or if the SDN domain does not have any traditional MobilityFirst router in it, and it's all just OpenFlow switches, then I guess there would be no harm in setting up flows in which the hop ID remains the same for the entire flow.
Just one comment there. If you go back to the first one, right? Just in the same graph. The first one is address-based forwarding,
Right.
and the second one is GUID-based. So the first one, the addresses don't change. So if you have a rule, you can just look at the destination address and keep forwarding, as long as you have the destination address in the packet. But the GUID-based forwarding, you assume that the identifier can attach at different points
to support mobility.
Right.
So there is a trade-off here probably, right? Because
Yes.
if it is a fully, and by the way, your 500 megabit per second, why is it 500 megabit per second? So a couple of things on the graph. The 0 on the x-axis should be 10 to the power 0, right? Because it's a 1 kilobyte.
Right.
Right, so 0 doesn't make sense. Second question is, the red curve, right? Why is it 550? It's a regular flow, right? It should be a gigabit or 800, right? Even if it's a kilobyte packet. Why does that matter?
Okay.
Even a kilobyte packet should be able to give you on a gigabit link. It should be able to give you higher. So there's something maybe you can look at later.
Right.
That is the performance of OpenFlow as it
Oh, I
has
see.
been
Okay.
delivered to
Okay.
us, and
Okay,
OpenFlow
okay.
doesn't guarantee you line speed.
I see. Okay.
But also there is this is the hop protocol that we're implementing, so it's a reliable, right? So
Yeah, so
so
I
the
think
red curve is the hop.
the
It's
drop
not
here
the-
is because for every chunk we involve that one round trip time in which it goes to the destination and then it receives an ACK and then sends 1,000 packets. And
I see. Okay.
so essentially, if you had 1 kilobyte package, each packet would go to the destination and then you would receive an ACK, and then you send the next packet, you receive an ACK. So it's that RTT delay which causes a decrease in throughput.
For small chunk sizes, it makes no sense. I mean, the overhead is too much.
Right. Yes.
It was meant to be for a
Large
yeah.
chunk sizes. But I think there is an interesting trade-off here in terms of how often you would do the controller update was, because you could potentially predict or do something more clever.
Yeah. Right.
Ideally, you don't want to do like a static way to do it.
Right, so potentially you could set up proactive flows. When you receive a chunk, you could set up proactive flows for the next 3 or 4 chunks and sort of assume that the next 3 or 4 chunks are definitely going to go through that path and the destination is going to be up on the same link.
And you could be wrong.
Right, exactly. So that's the... So,
This is the SDN controller control the path. If like a destination change the location, can controller change the path on the
right,
fly?
so you can remove...
Right?
Yeah, on the fly you can, as soon as you receive a notification from the switch saying there has been a dissociation, you can make changes to the flow rule, like removing a flow rule or inserting a new flow rule through some other path or anything like that.
Yeah, but the source doesn't need to.
Yeah, the source doesn't have to worry about...
Right.
Right.
So you don't need to worry about the chunk. You have to how big the chunk size is.
Right, the source doesn't have to worry about how big the chunk size is, but the whole architecture itself is such that one packet in each chunk has to go to the controller in order to ensure that we handle mobility, storage and all the other scenarios. And it's that one packet flow setup delay which causes a decrease in throughput for smaller chunks.
So I would say if it's the controller can change the path on the fly,
Right.
you don't need the first packet go to the controller to look up the changes, right? Because
Right, I think
Right.
we are not leveraging the power of the centralized view enough. Because if there is any change, let's just have a constant rule based on the source and destination. Whenever there is any change, the controller will get to know of it.
Right.
And then it can do a flow mod
Right.
proactively. Sort of.
Right. So
I mean, there's a trade-off on how often you update
Right.
the chunk rule versus do it. So I guess my question here was, did you try to match this? I mean, it seems like you're just going to say, how big of a chunk do I need to actually get the bandwidth?
right.
But you could try to model, like, how closely does this map to a very simple model, analytic model that says there's some, like circuit switching, where there's a fixed setup cost, and then there's basically a bandwidth overhead. So, the peak is a gigabit or whatever, or 900 megabits. And then if I know the setup cost, right, which you measured in a couple of slides before, does that simple model map to this experiment? I don't know if you could add that to the thesis. It's probably worth going through and seeing if that's true.
Yeah, sure.
Because if it is true, then people could try to either say, is that too high, or do we try to amortize more chunks, or do something else, where we do proactive paths or something.
I think that's very good.
But
Yes.
it seems like a very simple circuit model might capture.
Right, but it could also bring out issues within the OpenFlow control path, where there are, so we saw some strange additional delays that are happening when installing flow rules.
Right.
So, which may not be accounted in the models.
Well, no, you still want to do the experiment, but I'm just saying that
Right.
if the experiment's not matching the simple circuit model, then
Right.
things going on that shouldn't be happening.
Akash was saying, if you have a central visibility of a network, you don't need routing. You can just have a central controller that's all-knowing and decides what service you want, and you can write it as an application centrally. What we are trying to do here is to use OpenFlow to implement a compliant MobilityFirst protocol, which is not taking advantage of the centralization as much as it needs to, perhaps, but that's the trade-off. So people who have OpenFlow domain, they can do anything, and you can say goodbye to traditional routing protocol.
Oh, but you're saying mobility
But
first.
his
The protocol
task-
defines a per chunk.
Right, his task was to implement a MobilityFirst as is.
So the other experiment was to look at what ratios of GNRS traffic caused how much of a decrease in throughput, because obviously each chunk that needs to have a GNRS binding causes an additional delay at the controller. So the first line is no GNRS lookup, which is just GUID based flows, the same as what we saw in the previous graph. And so, and then from then on, the amount of the fraction of packets or the fraction of chunks that need a GNRS lookup increases. And at 80% GNRS lookup, we see that again the throughput is only about 550 megabits per second. So the controller having to map the packet to a network address is quite a significant overhead that we have here. And right now, if the controller had to hold the packet, or if it has to hold the packet in while the whole communication with the GNRS takes place, then that blocks further packet ends from being processed by the same module. Yeah. So I guess that's another future work, to have an optimized GNRS connectivity or an optimized GNRS lookup, which doesn't block any other flow that comes in.
Where is the GNRS sitting in this example? Like how far away or?
So in this, it's just a simulated delay at the controller.
Okay.
So each time we see a packet that has to be binded, we simulate a delay.
But that's still, you said it was like 80 milliseconds.
Milliseconds.
80 milliseconds. Okay, I see. Yeah.
Sort of a lower bound.
You
The
would
real
think-
delays we're seeing in orbit are closer to like 180.
No, but assuming like much touted round trip time is what, 100 milliseconds across the country.
Well, it's assuming you have these like 5 replicas, and you're using all 5 replicas.
Okay.
Yeah, and it's like sort of 100.
Right.
So that the theoretical the simulation result is about 100 for 95%.
Okay. Okay.
But the real one's probably.
But the real one has some reasons for that, because the topology is a little different compared to what they have.
Yeah, but
in mind.
then it's like really storing things in stable storage. I mean, it's a much more realistic,
Yeah.
like it's actually using stable storage.
Right. So one of the main bottlenecks that we have in this whole path is the switch CPU. So essentially, each time the switch receives a packet and it sees that the packet doesn't match any of the flow table entries init flow tables. It has to encapsulate the packet as an OpenFlow packet in and then send it to the controller. And this processing of fetching it from the data plane, creating an OpenFlow packet in and then pushing it out to the controller takes place in the switch CPU. And what we saw was that these switch CPUs are really low in power, and the amount of packet ends that they could process was only of the order of around 1100 packets per second. So that's quite low. So if we start sending packet ends at a rate more than that, then it just keeps dropping those packets. So
what kind of switch were you using?
this was a Pronto 3290. Right.
So even they are going to the same destination, they will just send all the packets?
No. So this we tried only to see how many packets the switch can process, and the upper bound was around 1100 packets per second for this specific switch. And there are a few research papers which look at this issue, and Dell, for example, came up with a solution where they added another CPU to the switch, another more powerful CPU, and they called it the split SDN data plane, and they used the larger CPU to sort of handle all these control plane processing, and the smaller CPU just does other tasks which involve the data plane, things like that. So, so this is again a big issue because each time it receives a flow mod, it's the switch CPU which has to extract the flow mod, get the contents out, and install the flow rule on the tables. And when that is happening, if it receives a packet that has to be sent to the controller, again, that could cause a delay because the CPU is already occupied doing something else. So, right. So
before the next result, so that's a great result, right? Because basically, again, you have a trade-off here. Like with mobility, you have to modify, but you know, a typical switch is not going to, is designed to not, it's a stable, like it's not expecting that you're going to modify it over 1100 times a second, right? So there's another interesting, I think there's a very interesting result.
Yeah, I guess in most SDN use cases like data centers or other places, it's all proactive flows where you actually know what flows you want, and there's very little load on the.
But having said that, 1100 times a second is not a small number, right? So
right, it's not a very small number, but
I mean, it depends on the number of flows going through.
Right, so in the static data center case, that's probably way enough.
Huge,
but if there's a lot of mobility, it's not clear.
And
I mean, actually, you know, within data centers as well, virtual interfaces is becoming, you know, very common use. So once you tear down virtual interfaces, you might be, you know, it's actually multiple flows that you throw away and put back together when you play with virtual interfaces. So I think even in data centers, you tend to see much larger variability in the flow set.
Yeah, right. If they're hosting another virtualization layer on top, that might start to look.
Pronto is, by the way, the cheapest switch.
Right. And that's great. I mean, I think you should go with the cheapest. Now the question is that, did you get a chance to look at, like, why is it 1100 packets per second? Is it actually, you hinted that it's the processor, and typically processor is roughly never a bottleneck in any computing system. It's typically the other things around it. The memory, it's the disk, you know, process typically always the fastest, right? Did you get a chance to look at that or not?
So I didn't get a chance to exactly look at what inside the switch is causing this bottleneck, but from some of the research papers that I read, it could be either because of the processor or the bandwidth between the data path and the processor itself.
Okay.
So the transfer,
the architecture of the switch.
Yes. So that seems to be the issue.
Can you write top on a switch?
I mean, that switch is running at 800 megahertz, probably single core power PC.
Okay.
It's not.
Yeah.
So actually you can.
Okay.
Yeah.
So that's pretty cool.
So it's the latest, I think Pronto is running the Debian. I think the latest
Oh,
software.
it's running Debian?
Yeah.
I mean, that processor is probably weaker than some of the higher end tools.
Right.
Single core.
Right.
800 megahertz.
That's why some of the other SDN work is trying to put some of the logic of the controller back to the switch.
Okay.
And so to reduce the number of things that needs to go. So the same logic through which a controller will decide what to do with it and what is, so try to push that some of it down to a local agent inside the switch.
I see. That will reduce the communication, but it will increase the computation requirements or some other requirements. So
Right.
I would
yeah,
think
so
that
maybe it won't.
I would think this is a very interesting way, because you say legacy switches, software controller. How would you do it in a real setting? And like no expensive stuff, just the cheapest stuff. How would you do it? I think technically it's very nice, interesting problem. Okay, so.
Right. So this experiment was to see what the effect of multiple flows is on the data path as a whole. So we experimented with the different chunk sizes of 1 megabyte to 10 megabytes, and what we did was one experiment with just one megabyte flow, and then another experiment with two 1 megabyte flows simultaneously, and then another with three 1 megabyte flows, and the same way for different chunk sizes, to see if there's any decrease in throughput with the addition of each flow. And we saw that with the addition of each flow, for 1 megabyte chunks, the throughput decreased by about 43 Mbps, and the amount of decrease per flow sort of keeps going down as we increase the chunk size. And this again seems to be some sort of a bottleneck in the control plane itself and not the data plane, because in the switch itself, if we run one iPerf for two iPerfs or three iPerfs, the throughput that we get between two different nodes doesn't vary that much, as in it remains the same over multiple iPerf flows. So this decrease in throughput has something to do with the control plane, and since the controller is able to handle packet ends in the order of 100 microseconds, again this could be something to do with the switch processing or the path from the switch to the controller itself. So that's probably another issue to look into for future work. Right. So in terms of how this can be extended, the first thing I guess is something that we discussed already, is potential optimizations to the design, maybe using some proactive flow setup and then modifying them if those flows don't work out and things like that. And to the Floodlight implementation itself, some simple protocols to handle storage and compute servers, and so those storage and compute extensions. And the other thing that I mentioned before is the controller GNRS connectivity, an optimal way to query the GNRS without blocking other packet ends that the controller receives in that time. And in terms of evaluations, there could be more evaluations done with large topologies and multiple switches to see what a real-life network, how a real-life network performs in this framework. And with the different kinds of traffic mixes, some of them having storage, compute, and those kinds of real-world traffic flows. So, so to conclude, we see that SDN is definitely a great platform for playing with experimental protocols or trying to implement new network technologies. And so SDN, OpenFlow functions. It also eases mobility management, like we saw, because every time there's an event at the switch, the controller gets notified, and that sort of makes mobility management and other routing functions simpler. But there also exist some restrictions in terms of how the switch hardware is implemented, and the current SDN protocols themselves in terms of how you can set up flow rules, which sort of restrict the way, or which restrict us from having an optimal SDN implementation. Like for example, if we had a MobilityFirst SDN switch, then we could set up flow rules on the address space using GUIDs and things like that. But so that's not possible as of now. But maybe as switch hardware evolves, we could have flows based on arbitrary header fields.